This is Talat Ahmad, Professor of Geology at the University of Delhi and presently the Vice Chancellor of Jamia Millia Islamia. We are going to discuss the Earth as a heat engine, about the partial melting within the Earth and how these partial melts, which are known as magmas, they differentiate to give rise to different types of rocks that we observe on the surface of the Earth. Let me explain to you what are these different portions of the part of the Earth. The Earth is subdivided into different shells, the inner core, the outer core, upper mantle and crust. So, we have the generation of core to start with at about 4.5 billion years, when there was a big bang, and then we had accumulation of nickel and iron in the core, and we had lots of heat that was accumulated, and then slowly there was differentiation of the Earth into lower mantle, upper mantle and finally the crust. As we all know that the crust of the Earth on which we live is the harder portion, which is solid, and it goes up to the depth of 30 to 40 kilometers, and we have upper mantle that is solid, but that keeps having small movement known as the convection of the mantle. So, the Earth to start with gets heat from two different sources. One is the extraneous source, that is the sun, and the meteorites that impacts the Earth, and the other one is the internal heat that generates because of the convection in the mantle, the presence of radioactive minerals, and also the residual temperature that was there during the core formation, and it is very, very hot. It is as hot as the surface of the sun, and even 20% extra heat is there compared to the surface of the sun. So, you can imagine that the Earth is a hot engine that works, and then how this heat is transferred. There are two ways of transferring the heat. One is by conduction, in which the heat is transferred, but there is no material movement. Okay? It is all through conduction. The other way of transforming heat is through convection, the best example being the convection that takes place in the upper mantle and lower mantle. So, to start with, I can show you the diagram which is shown here. As you can see here in the diagram, that the Earth is divided into different shells, the inner core or the solid core, then we have the outer core, which is a liquid core, then we have the mantle, and finally on the top of the surface is the crust. So, the crust is the portion where we live. This is about 40 kilometers deep, and from 40 kilometers to 2890 kilometers we have the mantle, which is convecting, as I told you before, and then we have a liquid core between 2890 and 5150 is the liquid core, which is again convecting, and then we have the inner core which is solid. This is from 5150 to 6370 kilometer. So, as I told you that in the beginning the core formed, and the core formed because of the big impact, and then iron and nickel, they got concentrated in the core, and the lighter material like the silicates and carbonates and all, they moved in the mantle, and finally from mantle to the crust. So, what we know is that this core portion is the area which is the hottest and which has more of iron and nickel, and then we have the mantle which is convecting. As I told you that heat can be transferred through convection or through conduction. The upper portion, which is known as the crust, is also sometimes called as lithosphere. Lithosphere is the uppermost part of the mantle and crust. Together up to 200 kilometers, we have the lithosphere, which is hard, and it cannot transfer heat through convection, but it can transfer heat through conduction. And the mantle, you have the convection which creates when convection cells, I will show you in the next diagram that there will be convection cells which actually drives the material or the process which is known as the plate tectonics. What you can see here in the second diagram is that as you go, this is the deeper and deeper, means this is the kilometer from surface 0 to 3000 kilometer. What we see here is that there is a steep, and this is the depth. So, the depth you can see is 3000 kilometers, and this is the temperature. So, initially with very little difference in terms of the depth, there is an increase in the temperature up to 2000 degrees centigrade, from almost 0 to 2000, and then there is a sort of adiabatic condition where there is a consistent increase in temperature, but not as high, with as high gradient as you can see in the upper portion of the crust or lithosphere. And then there is again a jump in terms of the gradient of temperature when it passes from mantle to core. So, this is the situation how the temperature of the earth is distributed within the earth. Now, I was telling you that there is something known as plate tectonics, which started with the concept of continental drift given by Alfred Wegener, which was based on the fit of different continents and similarity in the cuts of different continents, and then the more encompassing theory known as the plate tectonics came, in which you can see that this is a convecting mantle. The heat, whenever heat is transferred, okay, it goes from hotter to cooler place. So, it moves, and then this is convecting, but the upper portion, which is the lithosphere or the crust, it does not convect. So, what happens is this goes and hits the crust and pushes the crust on either side, this side and this side. So, this is also known as the ridge or the oceanic ridge. So, you will see lots of ridges in the ocean floor, in which new material from the asthenosphere goes here and forms a rock called basalt. So, new and new crusts are formed, okay, because of the partial melting that takes place in asthenosphere to form this basalt, and then this is pushed on either side. So when the material that comes first here is very, very hot, about 1200 degrees centigrade, and as time passes, as you can imagine, that on the top of this crust, we have some 6,000 kilometer high, 6 kilometer depth of water which is sitting on this. So as soon as it is coming here, it gets quenched and slowly it becomes cooler. So as this portion of the lithosphere gets cooler, it becomes heavier. So it moves as new and new material comes. These are moved on either side. So it goes and gets again subducted, because this is now very, very cold and heavy compared to the material on the underneath. So this is known as the subduction. So we have here, which is ridge, where the new crust is formed, and here this is the subduction zone, and as this material goes down, again it gets heated up, and then there will be melting again and giving rise to something known as the island arc. So this is how the earth works, with the inner core, outer core, lower mantle and upper mantle, the convection in the mantle bringing hotter material from deeper portion to the surface, and then this here it can interact with the water, get chilled, and then slowly becomes heavier and moves around to form the island arc. Now let us talk about how the melting takes place. See, what happens is there are 2-3 fundamental things for anything to melt, which is very common sense also, that either you increase the heat or you decrease the pressure, and third is that you add some liquid, some volatiles. So all the 3 conditions will allow the material to melt. So what you can see here, this is a part of the upper mantle, and this is known as the mantle plume. Mantle plume brings very, very hot material from depth, brings it to the surface. So the surface here on the top of it, this is a big plume. So this whole thing gets heated up and becomes a sort of bun, where it expands, goes up, okay, and then this place you will have generation of new magma, which will be coming out because of the new high temperature or increase in the temperatures. As you can see that this is the temperature increase, this is the depth increase. So what we see here is that this is something called as solidus and liquidus. So as this geotherm, this is the geotherm which I had shown you before. So when you bring this hot material, this geotherm is pushed towards right, it becomes heated up, and it interacts with the solidus, and then the melting occurs. Similarly, I also told you that we will have, when the subduction takes place, this material gets heated up, but as this material, which is basalt, when it interacts with the ocean floor water, it gets hydrated, and its melting point decreases because of the presence of water, and then this is known as hydrous melting. So here what we see is anhydrous, without presence of water, only you increase the temperature. Here you actually don't change much in terms of the temperature, but you add water to the system. So there is a continuous melting that takes place in the island arc system, and then you generate new magma here. Also you see and then because of that what we see is that this solidus remains same because the temperature does not change here, but this solidus moves left and cuts the this geothermal gradient, and then you have the melting in such cases. And the third case is that same as this, you bring very hot material, okay, which is known as the adiabat, and very high temperature material comes. Then there is you can see here the arrows which actually pushes these on the other side, and this oceanic ridge is formed, and oceanic ridge, along the oceanic ridge you bring new basalts or new rocks that will be generated in the upper part of the mantle. So what we essentially do is, in this case increase the heat, in this case increase the volatile content, and in this case you decrease the pressure because this new material comes, it pushes on either side. So here you will have a tensional zone. For the same temperature you will have melting that occurs. As we saw the last diagram, in which I talked about plate tectonics, I talked about continental drift, and I talked also about the condition under which partial melting takes place in the mantle. Same principle applies when there is melting taking place in the crust. Many times what happens is that instead of getting magma from the mantle supplies heat to the lithosphere, and because of the heat and then the pressure from the depth towards as you go shallower, it is called adiabatic uprise. So you will have high temperature material coming and supplying heat to the crust. So the crust starts getting extended, there is an extension in the crust, and the melting takes place in the crust. So now when the material is coming from the magma or from the mantle, it is giving rise to something known as the basaltic rocks. Whereas basalts, and even if you have higher degrees of partial melting, it can form ultramafic rocks like komatiites and peridotites, pyroxenite. And when the melting takes place in the crust, it forms rocks known as granite or granodiorite or lava flows, which is known as rhyolite. Okay. So basically, since different parts of the earth has different concentration, as I said that core will have more of iron and nickel, mantle will have more of magnesium and iron, and crust will have more of silica and alumina. So the rocks that will form under different parts of the earth will be different in terms of their composition. So when it is generated in the crust, it is forming silica and alumina rich rock known as granite or granodiorite, andesite, dacite, rhyolite. Whereas the magma that comes from the lower portion, that is the mantle, which is more rich in magnesium and iron, we will have something called mafic rocks, which is basalt, then peridotite, ultramafic rocks. Okay. So these are different type of rocks generated from different parts of the mantle because of the plate tectonic process. Plate tectonic process is which is based on the convection in the mantle and then breaking up of the lithosphere. As you can see that with time there are many records of formation of supercontinents, that many portions of the continent got together to form Gondwana land, Pangaea, and Rodinia at different times, and then with more and more heat coming from down by these mantle plumes, which broke these supercontinents. Say for example, our own India, which was part of the Gondwana land, was with Africa and South America, Antarctica, Australia, and because of the super plume, the Gondwana continent broke, and India, because of the convection that is taking place in the mantle, moved India towards north. So we were earlier much south of the equator near the southern pole. Now we are north of the equator. Okay. So by doing this, we will be generating more and more new oceanic crust, which is now known as, say, for example, the Indian Ocean. And when India moved north, part of it got subducted under the Tibetan Ocean, Tibetan plateau and crust. Okay. They gave rise to the island arc system, which is known as the Himalayan arc, where you will have rocks which will be generated more in the continental crust. So we have excellent record of formation of rocks that were generated in the continental crust, or the interaction between the oceanic crust and continental crust, giving rise to the famous Ladakh batholith, which I will be talking in another lecture. So these are big bodies that represents high temperature generation of magma in the continental crust. Now we discussed more about the plate tectonics and the consequent melting of the mantle and crust. Now what happens is, when this magma is generated, it undergoes changes which is known as the fractionation of magma, in which the minerals that different types of minerals. When it is a basaltic rock, okay, it will have a different composition. As I said, it will be mafic rock, where we have more magnesium and iron mineral will crystallize. So you will have crystallization of olivine, pyroxene, and amphiboles. Similarly, when it is the granitic rock which is generated from the crust, so there will be fractionation of granitic magma or sialic magma. This is sial means silica and alumina. So it will generate quartz, potash feldspars, plagioclases. So like that, you have different magmas evolving into different rock types based on the different minerals that they will crystallize and fractionate. Say for example, now I will show you this diagram. As I discussed earlier, that the magma is generated from either the crust or by melting of the mantle. So you can see in this diagram how things change in the magma. So this is the magma body which can get emplaced. Okay, sometime it comes out of the surface, then they are known as the volcanic rocks. When it doesn't come to the surface, they get frozen at some depth. It is known as the plutonic rocks. So what happens is, when the magma is placed, it is going to interact with the surrounding material. See here, you will have the country rock, so it will interact with the country rock and change its composition. Similarly, as I told you that many times there will be another magma which may be also present in the same area. So, there will be something known as the magma mingling or magma mixing. The third way of change in the composition of magma is through crystal and liquid. So, which is known as the fractional crystallization. So, here you will have magma which cools down. As it cools down, new crystals will form which will sink, because crystals will be heavier than the liquid. So, crystals will sink and form different rocks which will be also known as the layered complexes. The other way to differentiate the magma is also through some process known as the liquid immiscibility. So, in this, the magma itself splits into different parts like silicates and some of the carbonates, okay, or some of the mineral deposits, they form because of this liquid immiscibility. So, magma, when it is once it is generated, this is undergoing differentiation by different processes, as I explained. Now, if the magma comes, this magma comes from the asthenosphere or the mantle, then it is going to be more mafic magma. It will generate crystals which will, to start with, it will be olivine. If lots of olivine crystals form, they will settle down and the magma composition will change to new magma. Again, there will be another series of other minerals, pyroxene and amphiboles. They will fractionate, so they will form another layer, so like that. And then finally, what you have on the top is more of plagioclase, that it will have plagioclase, pyroxene, olivine, amphiboles. So, all these, and similarly, if the rock magma is generated in the crust of the earth, then you will have granitic melt or granitic magma, which will start fractionating potash feldspars to start with, and then quartz, and then some of the accessory minerals in the form of biotite, muscovite, and sometimes amphiboles. So, this is how things will change. So, now you can see another diagram to explain. Say for example, this is the primary magma, the magma which is generated. So, when it starts evolving, when it starts fractionating, the material which will crystallize, say for example, olivine will come here and the composition of magma will move this way. So, this is the original magma. When you fractionate out the solids or the crystals, the composition of magma will go towards C. So, this is how it is compensated. If you mix C and B, you will come to the composition of A. Similarly, there are possibilities that you can have two magmas which will mix and come to a third composition. So, it will be known as the magma mixing. And then another way is, this is in terms of the partial melting. So, a melt to start with will be here, this is the source. So, if you have the first rock or the hard rock which is melted, the first composition that is going to be will be very, very far from the source. And then as you increase the degree of partial melting, it will come closer and closer. So, to start with, if you have a source within the mantle, then the first melt that will be formed will be more basaltic, okay? And then as you will increase the degree of partial melting, you will have more and more magnesium rich basalt, and ultimately you will have something known as picrites and komatiites. So, this is how the composition of the magma changes by different degrees of partial melting, and then these individual melts can fractionate as I have shown here. So, as we discussed that how the magma is generated and then how the magma changes its composition by using the different diagrams. So, what we see is different magmas, composition of magma can differentiate by different processes to give rise to large variation in the composition of rocks that is seen as igneous rocks on the surface of the earth. Whether it is plutonic rock when it is crystallizing at the depth, and volcanic rocks when it comes to the surface and crystallizes. Now, let us summarize that we have discussed during this lecture is about how the different heat sources are available for the earth to generate magmas. Magmas are the liquids that is formed because of the melting of sources in the mantle, sources in the crust, and then how this magma changes its composition because of different methods of fractionation, fractional crystal fractionation or liquid immiscibility, and then we observe the diversity of the rocks of the igneous type which we observe in different conditions. I will be discussing in the next lecture more towards the different tectonic settings under which these rocks are formed.